All right, in this lecture, we're going to go over how to derive our stiffness matrices. So the weak form that we developed previously is equivalent to differential equation over an element, and it also contains the natural boundary conditions. The finite element approximations that we made are interpolants of the solution. So by substituting our linear or quadratic approximations into the weak forms, we get the necessary algebraic equations among the nodal values for Qi and Ui. In order to develop the finite element model based on the weak form, we have to decide the degree of the approximation prior to starting. So the finite element model can be developed for an arbitrary degree of interpolants. So we're just going to do it generically by assuming that U is approximately UH, which is the sum from j equals 1 to n of uj psi j. Where psi again is our interpolation functions of degree n minus 1. For n greater than 2, the weak form needs to be modified to include non-zero secondary variables at the interior nodes. So instead of carrying out the integration by parts during step 2 of the weak form development over the entire element, it's instead carried out over smaller increments, mainly 0 is equal to the sum y equals 1 to n minus 1 of xi plus 1 of a dw dx du dx plus c wu minus wf dx minus w of x a du dx from xi to xi plus 1 which is equal to the integral from x1 to xn of a dw dx du dx plus cwu minus wf dx minus w of x1 minus a du dx at x1 minus w of x2 times a du dx at x2 minus, this will just keep going until we got to minus w of xn minus 1 minus a du dx of xn minus 1 minus w of xn a du dx for my a of xn. Now we have to account for stuff entering and leaving on both sides of our nodes. So we get the original part of our equation and our first node don't change. All right. What does change is we now have minus w of x2 times a du dx of stuff coming in from the left minus a du dx of stuff coming in from the right of point 2. And this would keep going. We'd eventually have minus w of xn minus 1, a du dx at xn minus 1 from the left, minus a du dx xn minus 1 from the right, minus w of xn. We've now made it to the other side of our domain, a du dx at xn. So we're going to name this q. And what we get is that the integral from x1 to xn of a dw dx du dx minus cw plus cwu minus w of f dx minus w of x1 qe1 minus w of x2 q2 minus so on and so on. So we have minus w of xn minus 1, q of n minus 1, minus w of xn times q of n. As a reminder, so q1 is minus a du dx at x equals x1. This is important. Q2 would be a du dx at x2 left minus a du dx at x2 right. And Qn is a du dx at xn. So the values of q1, 2, 3, all the way on to n denote the jump in the value of our secondary variable going from the left to the right of the ith node. If no external source is applied, this node value is 0, much like when we were doing discrete systems, and if there was no applied force, the sum of the forces at that node were equal to 0. So lo and behold, we get a nice compact form for our weak form. We have 0 is equal to the integral from xa to xb, or x1 to xn, of a dw dx du dx plus cwu minus wf dx minus the sum from j equals 1 to n of w of xj qj. So Q1 or QA and QN or QB are the unknown point sources at our n domains. All others are specified point sources, if any, at the interior. So typically Q2 to n minus 1 are going to be 0. So now we're going to develop the finite element model for our original ODE. When n minus 1th degree Lagrangian polynomials are used as our approximation function. We're also going to use our interpolation function as our weight functions. Why not? Polynomials are fun. So by doing this, we're going to obtain n algebraic equations that we're going to use to represent our system. So what are we going to get? So W is going to be psi 1, psi 2, psi 3, so on until we get to psi n minus 1, psi n. So we're going to get equation 1. 0 is equal to the integral from xa to xb of a d psi 1 dx times the sum from j equals 1 to n of uj d psi j dx plus c psi 1 times the sum from j equals 1 to n of uj psi j minus psi 1 f dx minus the sum from j equals 1 to n of psi 1 xj qj. So that's equation 1. Noting that u is equal to the sum from j equals 1 to n of uj psi j of x. As a reminder, so this is dw dx, this is du dx, w, u, w, w. So then we get equation 2 and equation 3 and equation I. We get to equation n. So the nth equation would be 0 is equal to the sum, so 0 is equal to the integral from xa to xb of a d psi n dx times the sum from j equals 1 to n of uj d psi j dx plus c psi n times the sum from j equals 1 to n of uj psi j of x minus psi n times f dx minus the sum psi n of xj qj j equals 1 to n. So what am I doing? Extending this to account for multiple elements and multiple nodes and multiple points. So we now have algebraic equations for our system, and we can write them as 0 equals the sum from j equals 1 to n of kij uj minus fi minus q is equal to 0, where I is equal to 1, 2, 3 to n. So we're defining, basically we're at the same kind of equation we were using in discrete systems. So we're defining kij to be equal to an integral from xa to xb of a d psi I dx d psi j dx plus c d psi I, plus c psi I psi j dx, and we're defining fi to be equal to the integral from xa to xb of f psi I dx. Again, we're using our interpolation functions. Q is equal to the sum from j equals 1 to n of psi I of xj qj. So if we were to expand these summations, we would get K11, U1, plus K12, U2, plus K1N, UN is equal to F1 plus Q1. We'd get K21, U1 plus K22, U2 plus K2N, UN is equal to F2, Q2. If we keep going, we can fill in our matrix. And we get to Kn1, U1 plus Kn2, U2 plus Knn, Un is equal to Fn plus Qn, which if we were to write in a matrix notation is Ke times U is equal to F plus Q. Lo and behold, we're back at the matrix system of equations that we were using for a condensed system and the whole point of what we were trying to build. So our K matrix again is all our stiffness coefficient, is all the coefficient matrix or the stiffness matrix. The column vector F is a source vector or a force vector, and Q is our natural boundary conditions. So we need to take a closer look at our stiffness matrix and our source vector matrix, because we have to evaluate these. For a mesh of a linear element that's located between points XA and XB, or E and E plus 1, depending on how you want to write it, we'd have Kij is equal to the integral from XE to XE plus 1 of A d psi I, d psi j, plus C for that element, psi I, psi j, dx, and we'd have Fi is equal to the integral from xe to xe plus 1 of Fe psi I dx. Or if we wanted to use our local coordinate system, which again by definition is x is equal to x1 plus x bar, so dx would be dx bar. I'm noting that d psi I dx is going to be d psi I dx bar. We're going to get that Kij is equal to the integral from 0 to h of A d psi I dx bar, d psi j dx bar, plus C psi I psi j dx. And F is equal to the integral from 0 to h of Fe psi I dx. So we have to evaluate these integrals in order to be able to solve our system of equations. The good news is we're going to do this once and only once, and then we're going to be able to use the answers for the rest of the course. The bad news is you're going to be evaluating them for homework. So let's start with K11. So K11 would be the integral from 0 to h of A times, it's going to be the integral from 0 to h of A times minus 1 over h minus 1 over h plus C times 1 minus x bar over h times 1 minus x bar over h dx bar, which is equal the integral from 0 to h of a over h squared plus cx bar minus cx bar squared over h plus c over 3h squared x bar cubed. Sorry. Just looking at the answer. Plus c times 1 minus 2x bar over h plus x bar over h squared dx bar, which is equal to a x bar over h squared plus cx minus c x bar squared over h plus c x bar cubed over 3h squared, evaluated from 0 to h, which is a over h plus 1/3 ch. Similarly, k12 will be the integral from 0 to h of a minus 1 over h, 1 over h, plus c times 1 minus x bar over h times x bar over h dx bar, which is equal to minus a over h plus 1/6 ch, which is also equal to k21, which is what causes our symmetry. Don't believe me? Do the math. So lastly, we would need k22, which would be the integral from 0 to h of a times 1 over h times 1 over h plus c x bar over h, x bar over h dx bar, which is equal to a over h plus 1/3 ch. We need to do a similar thing with a source vector. If our source vector is a constant, you would get f1 is equal to integral from 0 to h of f times 1 minus x bar over h dx bar, which is 1/2 fh. And you get f2, which is equal to the integral from 0 to h of f times x bar over h dx bar, which is 1/2 fh. If FE, if our function is not a constant, we have to evaluate this integral every single time we work on a problem. So if we combine our equations together, we get that our stiffness matrix is equal to a over h times 1 minus 1 minus 1, 1, plus ch over 6 times 2, 1, 1, 2. So it's very similar to what we had previously for discrete systems. We didn't have a c term in those cases. And f would be equal to fh over 2 times 1, 1, again, assuming f is a constant. If f is a function of x, as it is in most cases, you have to evaluate the integral for every single problem. I'm not going to worry about if it's a function of x or not. So this is your stiffness matrix for a linear interpolation function. So if we are solving a problem in the future and it says assuming 10 linear elements, you were allowed to go to this equation and plug in a and h for those problems and run with it. You do not have to rederive everything over again. Well, if I did it for a linear element, I can do it for a quadratic element. For a quadratic element, we're still going to have the same integral. We're going to have k ij is equal to the integral from 2e minus 1 to 2e plus 1 of a d psi I dx d psi j dx plus c psi I psi j dx, which is equal to the integral from 0 to h of a d psi I dx bar d psi j dx bar plus c psi I psi j dx bar. F would be equal to the integral from 0 to h of psi I f dx bar. So again, we would have to evaluate all of these integrals. K11 would be the integral from 0 to h of a minus 3 over h plus 4x bar over h squared minus 3 over h plus 4x bar over h squared plus c times 1 minus 3x bar over h plus 2x bar squared over h squared times 1 minus 3x bar over h plus 2x bar over h squared dx, which gives you 7/3 a over h plus 2/15 ch. K12 would be the integral from 0 to h of a times minus 3 over h plus 4x bar over h times 4 over h minus 8x bar over h plus c times 1 minus 3x bar over h plus 2x bar over h squared times 4x bar over h 1 minus x bar over h dx, which gives you minus 8/3 a over h plus 2/30 ch, which again is going to be equal to K21 because of symmetry. And this would go on and on. You can do a similar thing for f. Again, if f is a constant, if not, if f is a function, we have to do it for every single problem. We would get f1 is equal to the integral of from 0 to h of f times 1 minus 3x bar over h plus 2x bar over h squared dx bar, which equals 1/6 fh. F2 would be 4/6 fh, and F3 is going to equal F1. So for our quadratic element, our stiffness matrix becomes A over 3h, 7 minus 8, 1 minus 8, 16 minus 8, 1 minus 8, 7, plus ch over 30 times 4, 2, 1, so 4, 2 minus 1, 2, 16, 2, minus 1, 2, 4. Again, if I say solve a problem that has 100 quadratic elements, you're free to use this stiffness matrix without any math. And F would equal FH over 6 times 1, 4, 1. We are one step away from solving a full problem. At this point, we have a set of algebraic equations for an element. We needed to generalize it for multiple elements and put them all back together and look at their connectivity. And then we will actually go through and solve a problem.